Good. Did anybody else learn anything yesterday that they want to share? Favorite energy? Anybody? Thermal energy? Kinetic energy? That's the energy associated with motion. Potential energy. We have a few, and we will talk about those today. Okay, so has anybody seen The Office in here? Yeah? So Dwight, he's a little bitter guy. You guys may think you're working from a desk, but as you are just sitting there, you're actually not doing any work, right? Because work is force times distance, so if you're just sitting there, not taking notes or anything, you're just motionless, you are not working, even though your brain may be working. And there will be work going on inside of your brains of like the neurons and stuff being communicated, but if you're just sitting there motionless, from an outside observer, you are doing no work. Okay, so to do work, we need to move a force a particular distance. Okay, and we'll talk about that more today. Okay, so you guys have just some practice problems right here. So let's take the next couple minutes just to try these, please. Okay, so the first one, anytime that you guys are solving a word problem, what is the first thing you're going to do? Write down what we know, for sure, okay? So, we know a car is traveling at 25 meters per second east, and then it applies the brakes and stops. So my initial velocity is 25 meters per second east. It applies the brakes and stops, so if it's stopping, my final velocity is 0 meters per second, and my time is 5 seconds. Okay, we're asked what is the acceleration of the car, okay? So from our formula sheets, we know that acceleration is equal to VF minus VI over the change in time. We know all of these, so we can just plug it into our formulas. So we have 25 meters per second minus 0 meters per second divided by a time, which is 5 seconds. So 25 minus 0 is 25 meters per second divided by 5, which is going to be, sorry, I did that backwards. Sorry, my VF is 0. Yeah. Smartboard's being funny today. Okay, so VF is 0 meters per second, and my initial velocity is 25 meters per second. Okay, so negative 25 divided by 5 is negative 5.0 meters per second squared, right? Our units, we have meters per second divided by seconds, so we get meters per second squared, and because acceleration is a vector quantity, we should give it a direction as well, okay? So that one was done really well. This second one here, so an object is starting at rest, so my initial velocity is 0 meters per second, and it accelerates at 2 meters per second squared east for 10 seconds. What is the final velocity? Okay, so we have acceleration, we have an initial velocity and a time. So let's use our acceleration formula again. Acceleration is equal to VF minus VI over t. We're looking for this VF. So how are we going to get VF by itself? Well, we have a fraction. Okay, so the first thing we need to do is get rid of our fraction. Okay, so if we are dividing by t, the opposite of dividing by t is multiplying by t. Are we going to do that to one side?
Both sides.
Both sides. What you do to one side, you have to do to the other. That is grade 7 algebra. Okay? So, now we have t times a is equal to VF minus VI. Okay? What is my last step to getting VF by itself? Adding VI to both sides, right? Add VI plus VI. So negative VI plus VI cancels out. And now we have VF is equal to, and I'm going to put these in brackets because I don't want us to get this far and get the wrong answer. Okay, VF is equal to T multiplied by A plus VI. Okay, we want this to be in brackets because we want to multiply time and acceleration before we add VI onto it. Okay, so at this point we know time, we know acceleration, and we know our initial velocity. So VF is equal to 10 seconds times 2 meters per second squared plus 0 meters per second. Seconds divided by seconds squared gives me meters per second, which is good because those are the units for velocity. And then we get a final velocity of 20 meters per second east. Okay, 2 digits here because we have 2 sig digs in the question. Okay, so let's not forget about our sig digs. Okay, hopefully, I don't know, on a scale of 1 to 5, how did we do on these 2 problems? 5 was that I got both of them. 4 was I made like a little mistake. 3 was anything less than 3 is I need help. Okay, cool. All right. So if these 2 problems are difficult, you need to come and see me so we can get you sorted out before you move any forward, okay? These types of problems are similar to what you will see on your physics unit test, okay? Which is April the 1st, next Thursday. Okay, so without even doing any calculations, I just want to ask you guys, are these motions positive or negative acceleration? So what is positive acceleration? Yeah, so if we're increasing our speed, right? Yeah, perfect. So in this case here, we're going from 5 meters per second east to 15 meters per second east. So is this negative or positive acceleration? Positive, okay? So positive acceleration. And the second example here, we're going 17 meters per second, and then we slow down to 12 meters per second. So is this positive acceleration or negative? Negative acceleration, good. Okay, so if you get a question where you have negative acceleration, it's okay. Okay, it's okay. Just hopefully in the question, the object is slowing down. Okay, so when you get your answer, just look at your answer and look at the question and ask yourself, does this make sense, right? If the object is speeding up, you should not have a negative acceleration. Okay, good. So this brings us into our new content. So in general, a force is like a push or a pull acting on an object. Okay? So right now, the Earth is acting a force of gravity on me and all of you, right? So it's pulling us downward to the ground, right? If we were in outer space, where the force of gravity is much, much lower than it is on Earth, then you would have less force acting on you, right? Okay? Force is measured in newtons. Okay, these are the fundamental units of a newton. Okay, don't worry too much about that. Okay? But you just need to know that a newton is moving a mass by the acceleration. Okay? So that's how we get kilogram per meter per second squared, and that is a newton. Okay, so if you are accelerating a mass, you have a force, right? So if you're driving your car and you put your foot on the gas pedal, you are applying a force, or your car is applying a force on the ground, which allows it to move forward. Okay, force is equal to mass times acceleration. What do you guys see on your formula sheet? Do you get Oh, you don't even have it on there. You guys won't be using this too much, but force, if you take physics 20, you'll see force is equal to mass times acceleration. F equals ma. This is Newton's second law. He has 3. Actually, he has more than 3, but that's okay. For the sake of science 10, this is all you need to know. And if you're interested in Newton, take physics 20. Okay, good. So, work is when you are moving force, right? So, this desk, it's being forced, like it exerts a force downwards, right? The acceleration due to gravity is pulling the desk down, right? Okay? Now, if I want to do work on this desk, not the type of work that you guys are doing, right? If I want to do like physics work, I need to move this desk at actual distance, okay? And that can be measured in joules, okay? Is moving a force a particular distance, okay? So if this force, I don't know, it feels probably like it's 20 kilograms, okay? So I'm moving this desk, we can calculate the newtons, but that's okay. Okay, if I move this a particular distance, I am doing work on the desk, okay? To move things, you need to put work into it, right? Like right now, the notes are not writing themselves, right? So you guys need to do work to write this stuff down. Okay. So work is done when energy leads to a change in the position of an object. So I need to put energy into moving that desk, okay? And the desk needs to move, okay? If I'm like pushing on this whiteboard and it's not moving, so my distance is 0, do I have any work? No, right? Because I need to be moving it. I could push on this all day, I'd be wasting my energy, right? But I would not be doing any work on the wall. Does that make sense? So you need to be moving something to be doing work on something. All right, there we go. Okay, so conditions for work. 1, there must be movement, like we just talked about. There must be a force, and the force and the distance the object travels must be in the same direction. Okay, so in this example you have up here, if you are pushing on a box, and if the motion of the box is in the same direction of your force that you're applying, then we say we have done work. In this second image here, okay, this student has a backpack on, okay? So the force of the backpack is acting downwards, right, because of gravity. This person is applying a force on the backpack to keep it around their shoulders, right? And you guys can probably feel that when you're walking with the backpack on. And if you have a few textbooks in there too, it'll feel heavy, right? But because you are applying a force upwards on the backpack, and the backpack is not moving, right? So, like it's not moving up or down, so distance is 0, right? Are you doing any work on the backpack? No, right? Because we're not lifting the backpack anymore, it's just kind of on, okay? And if the person is walking in this direction, the force and the direction of the motion are not in the same direction, so no work, okay? Again, the force and the direction of the motion must be in the same direction. So is there work here? No work. Okay, this third example. This person is lifting up a bag of groceries. Okay, so the bag of groceries is exerting a force downwards. That's the force of gravity. So to move that bag of groceries, this person needs to put energy into lifting the bag of groceries. and they are in the same direction. So do we have work here? Yes, we do, for sure. Once this person has picked up the bag of groceries, okay, so they've already lifted up here, and maybe they're walking inside of their house, are they doing work on the groceries? On the groceries, right? We're not lifting the groceries, right? We're doing work moving towards our house, right? But on the actual groceries themselves, because the motion and the direction of the force is not in the same direction, there is no work. Okay? So, the force and the distance the object travels must be in the same direction. Okay, that is important. Okay. So, a weightlifter raises a barbell, distance of 2.4 meters. Okay, so this is a word problem. What is the first thing we do when we have a word problem? Yeah, write down the variables, right? What do we know? Okay, well, we know the barbell is being lifted a distance of 2.4 meters. So D is equal to 2.4 meters. If the average force required to lift the barbell is 2.00 times 10 to the 3 newtons, okay, we are asked, what is the work done? Well, we already talked about work being moving a force a distance. Okay, this weightlifter is doing work by applying a force of 2 times 10 to the 3 newtons, a distance of 2.4 meters. So my work done is I don't know that one. 2,000 times 2.4 is 4,800, I believe. Times 10 to the 3. Perfect. So work is equal to 4,800 Newton. Okay, so our units here. So if we're multiplying a Newton and a meter, our units are going to be Newton meters. Okay? Does anybody know what a Newton meter is? What did we say on the last slide that work was measured in? Joules. Okay, good. So a joule is a Newton meter. So work is equal to 4,800 joules. Why am I not done here? Sig digs, for sure. Okay, we have 3 given in the question, and we have 4 here. So you can either put this into scientific notation. So 1, 2, 3. 4.80 times 10 to the 3 joules. Or you could put this into kilojoules. Okay? So just like 1,000 grams equals a kilogram, 1,000 joules equals a kilojoule. Okay? So this is also equal to 4.80 kilojoules. Okay, I have no preference if you guys use scientific notation or you change the units on that. Okay, that's totally fine. What I do have a problem with is if you leave your answer without the proper amount of sig digs. Okay, that is not okay. Okay, good. Okay, good. So that was work. Okay, now we are going to talk about energy. Okay? So we need energy to be able to do work, right? You know how you guys are tired at the end of the day and you don't feel like doing any work? Well, it's probably because you're low of energy, right? So you need energy to be able to do work. If you do work, you lose energy, right? So if I'm like doing a bunch of reps and I'm lifting weights up and down, I need to put energy into lifting those weights, right? And if you have work done to you, you gain energy. So if you're at the bottom of the hill and you're really tired and your friend gives you a piggyback up the hill, right? You're going to be gaining potential energy. So a change in energy is the same thing as doing work. Those things are equal, okay? Change in energy is equal to the work done, okay? So in the last example, the weightlifter, he put in 4.8 kilojoules of energy to lift that barbell. Now that barbell will have 4.8 kilojoules of potential energy, right? Change in energy is equal to the work, okay? And what that looks like, change in energy, so delta E. Remember, anytime that we have a delta, it change, so change in energy is equal to work. Okay, I also added some formulas to our board over here. Okay, so we have energy is equal to work done, and we also have kinetic energy and potential energy on there. And we will get to those. Are there any questions so far? Great. Okay, so without even doing any calculations, based off of this formula that we just talked about, change in energy is equal to work done. So, if a weightlifter does 4.8 times 10 to the 3 joules of work in lifting a barbell, how much energy is gained by the barbell?
4.8 times 10 to the 3 joules.
Yeah, perfect, right? We know that the work done is 4.8 times 10 to the 3 joules. And we know that the change in energy is equal to work. Therefore, if you ever see 3 dots like that, that means therefore. Okay? So therefore, change in energy is equal to 4.8 times 10 to the 3 joules. Okay. So work and energy. Work is moving a force a particular distance, and the change in energy is equal to work done. Okay? So there are some connections here. Okay, so yesterday you guys learned about different forms of energy, right? So I'm not going to go into this too much, but other than the fact that there are a lot of different forms of energy, right? We have electrical energy, which is allowing us to sit in a lighted room and watch a smartboard and all that kind of stuff, okay? We have electromagnetic energy. So that is energy that allows us to use our cell phones, right? Our cell phones are broadcasting radio waves from our phones, right? Which are interacting with the cellular towers. So there's interactions of information there. We have thermal energy, as we talked about earlier, so melting ice cream, heating soup. Mechanical energy is a combination of kinetic energy, so motion of movement, and the potential energy due to your position above Earth's surface. Okay, So don't worry too much about that. We have nuclear energy. So this is what powers nuclear power plants, right? Nuclear fusion occurs in suns, stars. This is what allows us to not freeze, right? This is what allows us to live. And then we also have chemical energy. So that's energy that's like stored in your juice box, right? Your food is in a particular orientation. When you digest it, when you break those bonds, energy is released, and then your body uses that, okay? Striking a match, right? There's chemical energy in that sulfur, typically. When you provide a spark to it, right? When you provide a spark to it, then it gives it that little initial energy for that rest of that match to light up. Okay? So chemical energy, so this is potential energy. So potential energy, just in general, is the ability to do work. Okay? Potential energy is the ability to do work. Okay, so when you eat food, and let's just talk about glucose. This is what glucose looks like on a molecular level. Okay, if you take 520, you will look more into that. Okay, when you digest food, these bonds are going to be broken. When bonds are broken, energy is released, and your body takes that energy for whatever it is, right? To like walk around, to digest food, to grow, to move in your environment, okay? We'll talk more about that in the bio unit. We have electrical energy and magnetism. So this is the work done by moving charges. So right now we have electricity, electrons, which are flowing through wires, producing light. Okay? That can do work. We have nuclear energy. This is pretty important for a couple of reasons. Again, so this is potential energy, which is stored in the nucleus of an atom. So when we split an atom into two smaller elements, kind of like a decomposition reaction, energy is going to be released. And when two elements combine in nuclear fusion, that's what occurs in the sun. Fission is usually like nuclear reactors. Or if you're studying like radioactive decay of a material, that is nuclear fission. Okay. Fusion is really important. This is the process of what is occurring in the sun. Give me your phone, please. Okay, so fusion is what keeps us warm, what allows Earth to have liquid, solid, and gas water. Right, that's really important that all three states of water exist on Earth. Okay, we have solar energy. These solar energy results from hydrogen nuclear fusion reactions, typically in the sun. Electromagnetic radiation produced from the sun converts to other forms of energy. So it can either be converted into like electrical energy, right? It can be converted to thermal energy. If you leave something out in the sun, it will warm up. We will talk more about solar energy and alternative energy production at the end of this week. Okay, we have thermal energy. So heat, when we say heat, this is the sum of kinetic energies of the atoms in the substance. So kinetic energy, okay, this is the energy due to motion. Okay, if you study kinesiology at university, it is the study of motion, right? So the study of how your bodies move. Kinematics is a study in this, or it's a discipline in physics which studies how objects move. Okay. And thermal energy always transfers from hot to cold. This is where we have a high heat concentration, okay, concentration brackets, and cold has low heat concentration. So it's always going to go from an area of high concentration to an area of low concentration. Okay. Yeah, we will talk about convection, conduction, and radiation in our last unit, in the Earth unit. Okay. And this image down here, this is showing the molecular makeup of either a solid, liquid, or a gas. Okay. We know that when solids are just kind of sitting there, they have low energy. So the molecules inside of the solid are not moving a lot, right? They're kind of like stuck in place. As we turn into a liquid, they're going to have a little bit more motion, but they're still going to be confined to the shape of their container, right? If I pour a coffee just on the ground, it will spread out, right? But if I pour it into a cup, it will stay in the cup. Moving up in energy, a gas is just going to move everywhere, right? It's not necessarily confined to one location, right? If you had a balloon and you did not tie up the end and you let go of the balloon, the gas is going to come out of the balloon, right? The gases, like heat, always want to go from an area of high concentration to an area of low concentration, right? Things always want to be in equilibrium as best as they can. Just like my coffee mug. Eventually, if I leave it there long enough, it's going to become the same temperature as this room would, right? That's equilibrium temperature. Okay, so moving into motion and energy. So we have kind of hinted at what kinetic and gravitational potential energy is. So here's the slide. So kinetic energy, again, the energy of motion. If an object is moving, it has kinetic energy. Okay? If an object is not moving, it has no kinetic energy. So kinetic energy, the formula you will see on your formula sheet is 1/2 mv squared. Okay, and if that fraction is bothering you right away, this is the same thing as saying 0.5 mv squared. Okay? And just be careful with this exponent here, because that only belongs to the velocity. Okay? It does not belong to that whole term. Okay? We are just squaring the velocity, not the mass, and not that 0.5 or the 1/2. Which is easier to like just look at, the 1/2 or the 0.5? Either? Same thing? Give me a thumbs up if 0.5 is easier to look at. Give me a thumbs up if the fraction is easier to look at. Okay. Just curious. Okay, so that's kinetic energy. Gravitational potential energy. This is the energy of an object based on its position above Earth. Okay, so formula for potential energy. So EP, so potential energy, is equal to mass times gravity times height. On Earth, the acceleration due to gravity is 9.81 meters per second squared. Downward, of course. We're not just all floating and caught on the ceiling, right? Gravity acts downwards. Okay, M is your mass. And H is your height. And G is the acceleration due to gravity. and that is on your formula sheet. Okay? Okay. Any questions about energy or work or forces? No? Good. I am by default always going to do 1 over 2 mv squared. So if it really bothers you, just let me know and I will do the other one. Or just know that the 1 over 2 is equal to 0.5. And the other one that we've talked today, potential energy is equal to mass times gravity times height. Okay? And again, I put those two formulas on our formula board over there, and it has it a little bit more explained, right? It just shows what your H is and what your M is and stuff like that. So if you're ever stuck on kinetic or potential energy, just refer to the sideboard there. Okay. Mechanical energy. This is the combination of both of them. Don't worry too much about this, okay? That is like Physics 20. I just wanted to introduce that today. One thing I wanted to talk about on this slide though is just the energy conversion that is occurring in this system, okay? So this is a pendulum. It's going back and forth and back and forth, right? Once it moves up here, okay, it's at maximum potential energy and zero velocity, right? If it's moving back and forth. Right before it falls back down, its velocity is going to be zero for a brief second, right? So as it moves back and forth, once it gets to the top of its motion, it has no kinetic energy and all potential energy. Once it moves down to here, it has no more potential energy. Remember, potential energy is that due to its position, right? So if it's at position 0, no height, then it will not have any potential energy. All of that potential energy has been converted to kinetic energy, okay? And then as it goes back and forth, that kinetic is being converted to potential, which is being converted to kinetic, which is being converted to potential, okay? Is that okay? Energy is just going to be converted from one form to another. So let's give you an example. So I have a pad of Post-it notes on this desk, okay? How am I going to get it up here? I got to lift it, right? Okay, good. So I pick it up, I'm putting in work. What type of energy am I giving it right now?
Potential energy.
Potential energy. If I hold it perfectly motionless, so it's not moving, how much kinetic energy does it have?
0.
0, right? Velocity is 0. So if velocity is 0, anything multiplied by 0 is 0, right? So if it's not moving, we have no kinetic energy. So we all agree that I have only potential energy up here, right?
Yeah.
What is going to happen to the potential energy as I drop it?
It's going to go down.
Yeah? And what's it being converted to?
Kinetic energy.
Kinetic energy, right? 0 kinetic energy. Right before it hits, it has maximum kinetic energy, right? So if my reference point is the desk, how much potential energy does it have right now?
0.
Good. How much kinetic energy does it have right now? 0. It's not moving, right? What does it have right now?
Maximum potential. 0.
Potential, right? Okay, so let's all go through this and say it with me. What type of energy do we have right now? Potential, okay? Before it hits, what kind of energy does it have? Kinetic.
Potential.
So I'm moving it, kinetic energy, right? Okay? Okay. Good. Thank you. Okay, we're gonna skip over this because we already talked about energy, so just disregard that. Okay, Potential energy, we have talked about this a lot today. Here's just some more information. So this is, again, stored energy that has the potential to do work, hence the potential energy. Okay, so there is gravitational potential energy. So that's like me lifting and lowering the post-it note, right? I'm giving it gravitational potential energy. It has elastic potential energy. So in this diagram right here, the person is pulling back a bow. He puts work into the bow to be able to pull it back, right? And if he doesn't let go of the arrow, or sorry, the drawstring, then he has potential energy, right? As soon as he lets go, what is that potential energy converting into? Kinetic, right? If that arrow starts moving after he lets go of the string, he's converting that potential energy into kinetic energy. Okay? Okay, Brody, I've been watching you drink that juice box all morning. What type of energy is in your juice box? Chemical potential energy, right? Good, good. So then you drink it, your body breaks up the little sugar molecules, right? And then you have energy to move around. And if you're moving, what kind of energy is that? Kinetic, right? Motion is kinetic, okay? Kinesiology, kinematics, okay? Anything that has like a K-I-N-E, kine, is motion, okay? Okay. Okay, I'm not going to spend a lot of time on this because we've talked about it a lot. So gravity pulls things towards the earth. So EP is how you might see it, which is right here, potential energy, gravitational. Yeah, so acceleration due to gravity is 9.81. So remember, EP is equal to mass times gravity times height. Okay, if you wanted to find the force of gravity acting on you, okay, you would multiply your mass by the acceleration due to gravity. Okay, you could find your weight in newtons if you actually wanted to do that. Okay, yeah. Mass versus weight. So your mass is going to be the same anywhere in the universe. Okay? Mass is measured in kilograms. Weight. Weight is your mass. Okay, so let me say this again. So weight is going to be your mass multiplied by the acceleration due to gravity at that location. Okay? So on the moon, you're going to have less weight than you would on Earth because the force of gravity is lower on the moon. Okay? If we were standing or hovering near Jupiter, because Jupiter is a gas giant, he probably can't stand on it. It's much larger than Earth, right? So it's going to have a larger gravitational influence. So would our weight be larger on Jupiter or would it be larger on Earth? Our weight. Larger on Jupiter, right? More acceleration due to gravity on Jupiter. Same mass, right? Same mass, different weight. Okay? The only way you can change your mass is by cutting your arm off or losing weight. Okay? Okay. Okay, we've talked about this. So I'll just move on from that. Potential energy is mass times G times height. So if you lift a book like 10 meters, you have given it potential energy, right? And you can calculate that. Okay, so what is the first thing we're going to do when we have a word problem? Write down our variables, okay? Because that is going to help us decide of which formula to use, okay? We've introduced a few formulas. We have velocity and acceleration. Now we have kinetic and potential energy, right? So it's a really good idea to put down our variables, and that's going to help us decide which formula we are going to write with, or solve the problem with. Okay? So a child with the mass of 25 kilograms. So mass equals 25 kilograms is at the top of a slide in an amusement park. If the vertical height of the slide is 4 meters, calculate the potential energy of the child relative to the ground. Okay, so we have mass, we have height, we're looking for potential energy. What is not given in the question, but we always know? Perfect, the acceleration due to gravity. And if the question does not say you're on Mars or Jupiter, okay, just assume we're on Earth, okay? So G is always 9.81 meters per second squared for the case of Science 10. Okay, the value of G is not actually the same throughout Earth. It depends on how far you are from the center of Earth, okay? But don't worry about that too much. G is always 9.81 meters per second squared for our calculations. Okay, so we're looking for potential energy, and we have G and H and M. So obviously we want to use our potential energy formula. So EP is equal to mgh. This formula is already written in terms of potential energy, right? So now we can just plug in our values and calculate our answer. So 25 kilograms times 9.81 meters per second squared times 4 meters. You put that in your calculator. You should probably get 981. Units. What are my units? What is energy measured in? Energy is measured in joules. Yeah, you bet. Okay, 3 sig digs, 3 sig digs. So this is good. And maybe you're asking yourself right now, how on earth do we get joules from kilogram meter second squared meter? Okay, so if we jump up to our fundamental units board, okay, don't worry too much about this. Okay, this is more important for Physics 30, but I thought it was actually helpful for us. A joule is a kilogram meter squared per second squared. Okay, and what have we done here? Well, if I just show my units, we did kilogram multiplied by meters per second squared multiplied by meters. Okay, so if you're doing this, you add up your meters because you can't just cancel them out, right? So meter times meter equals meter second squared, and a kilogram is just a kilogram. So we get kilogram meter squared second squared, which is a joule. Okay, you don't need to worry too much about the units, other than you need to know that energy is measured in joules. That's really important, okay? Energy is measured in joules. Okay, so you don't need to do this every time, but when you're calculating like kinetic energy or potential energy, just know that your answer will be in joules. Okay? All right. So, let's go through this like you just did. Okay? So, an 800-gram bird. So mass is 800 grams. Has 47 joules of potential energy. So EP is equal to 47 joules. When it is perched up in a tree. Okay, we want to find how high is this tree. So H is equal to question mark. What is not given, but we always know on Earth?
Acceleration.
Yeah, we know our G value, the acceleration due to gravity. Yeah, G is 9.81 meters per second squared. Okay, so we have mass, height, gravity, and potential energy. That's a good indicator. We should use our potential energy formula. EP is equal to mgh. But hold up. What is the question asking for?
H.
Height, right? So we need to get h all by itself. Right now it is being multiplied by mass and gravity. So the opposite of multiplying by mass and gravity is dividing by mass and gravity. And what we do to one side, we must do the other. All the grade 7s chant me when I say that. It's kind of fun. Okay, anyways, so H is equal to EP over mg. Okay, now when we are calculating a joule, what are the units for joules? Kilogram, meter squared per second squared. What units are our mass in right now? Grams. So what do we need to do to this? Convert it to kilograms. Good. So in 1 kilogram, we have 1,000 grams. So if I have 800 grams, I have 0.8 kilograms. Okay, and if you want to calculate that, it would look like this. 800 grams times 1 kilogram over 1,000 grams. Your gram unit will cancel and you will be left with 0.8 kilograms. Okay, now that our units are good, we can just plug this into our formula and solve it. So 47 joules divided by our mass, which is 0.8 kilograms, times the acceleration due to gravity. And my height is going to be, what units will that be in?
Meters.
Meters? How do you know that?
In this equation, you measure height in meters.
Yeah, perfect. Okay. So generally height is going to be given in meters, or if you're calculating it, if you have, like, you need to have everything in kilogram and meters per second for this formula to work. Okay? Otherwise, if you have like a gram meter squared per second squared, it's not a joule. Okay? A joule is a kilogram meter squared per second squared. Okay? So if you divide a joule by a kilogram meter per second squared, you'll be left with meters. You bet. All right. I know I've been talking for forever, but we're almost done, and you guys get tomorrow to practice. So, sorry. Elastic potential energy. So we talked about this already. If somebody has a drawn bow, it has elastic potential energy, right? As soon as he lets go of that bow, that potential energy will be converted into what kind of energy if the bow is shooting forward. Kinetic. Good. Okay? Excellent. chemical potential energy, we talked about this too. Okay, and our last topic for the day is kinetic energy. And we've talked about this a little bit. So this is the energy associated with motion. And to be able to allow something to move, we need to apply a force to it, right? If you play billiards or pool, right? The balls on the table are not going to move unless you shoot the cue ball at it, right? You got to do work to move those balls on the pool table. The amount of kinetic energy depends on the velocity and mass of the object, right? So kinetic energy is 1/2 mv squared. So what do you think will happen if we increase the mass? Will it decrease or increase the kinetic energy? Yeah, it'll increase it, right? It'll increase it, for sure. So like, if a small car was driving down a road and a big truck was driving down a road with the same velocity but different masses, the larger truck would have more kinetic energy. Okay? It would also require more work to get those big trucks moving to those speeds, right? This is why like big trucks require more fuel, right? They have not as good as gas mileage as a car would. Okay, so same thing. If we leave the mass alone, so if we have two identical cars, okay, and one is moving at a faster velocity or speed, which one has more kinetic energy? The slower moving car or the faster moving car?
Faster, right?
Yeah, faster moving car, right? For sure. And again, to get that car moving faster, you just need to apply more energy, right? For that. Good. Good. Okay, so kinetic energy formula, EK is 1/2 mv squared, or if you don't like that, you can do 0.5 mv squared. Mass needs to be in kilograms, not grams, and velocity needs to be in meters per second, okay? Otherwise, it will not be a joule. It would calculate like a microjoule or something, okay? Which we don't like. Okay, so make sure we're in fundamental units, okay, which is kilogram, meters, and seconds. Okay, those are fundamental units. Physics-friendly units is what I like to call them. Okay, meters, kilograms, seconds. Okay. Okay, so we have a practice problem here. What is the first thing that we do when we have a word problem? Write down what we know. Okay. A car has a mass of 1,500 kilograms. So mass is 1,500 kilograms. It is moving at a speed, I guess this should say velocity, if we have a direction, right? Moving at a velocity of 14 meters per second west. What is the kinetic energy of the car? Well, I have mass and I have velocity, and we're looking for kinetic energy. So let's use the kinetic energy formula, of course. Okay, and this formula is already written in terms of kinetic energy, so now we can just plug in our values. 1/2 times our mass, which is 1,500 kilograms, times our velocity, 14 meters per second squared. And remember, only the velocity is squared here. Okay? So when you guys are entering this into your calculator, I want you to do it like this. Put in 0.5 or 1.2, or 1/2. Okay, just use your brackets so you get the right answer. This is how you should enter it into your calculator, right here, okay? bracket 0.5 bracket, bracket 1500 bracket, bracket 14 squared bracket. Okay? Brackets are your friend and they will help you get the right answer. Okay, so if you put these into your calculator carefully, you will get a kinetic energy of 147,000 joules. Okay, how can I make my answer better? Sig digs, good. Okay, so we have 2 sig digs here and 4 sig digs here. So how many sig digs will my answer have? 2, right? You bet. So if our decimal is here, we need to change this number so it only has 2 digits, right? So let's move our decimal. 1, 2, 3, 4, 5 places. Okay? And we want it to have 2 numbers only. So what is to the left of that 4? It is a 7. So are we going to leave that 4 alone or round it up? Round it up, right? Good. So EK is equal to 1.5 times 10 to the 5 joules. All right. Questions? No? All right. We have one more, and then I'm done for today. You guys have been great. Okay. So again, first thing we're going to do when we have a word problem, write down what we know, for sure. Okay, a hockey puck has a mass of 0.17 kilograms. The hockey puck also has 73 joules of kinetic energy. What is its speed? Okay, so our formula, EK is equal to 1 over 2 mv squared. We need to write this in terms of V. Okay? So, the first thing you will do for this formula when we're trying to simplify for either mass or velocity is multiplying by 2. Okay? Do not try, well, you can divide by 1 over 2, but you have to be really careful with, because you're dividing a fraction, right? So when you're dividing a fraction over here, if it's 1 over 2, this is actually going to be multiplied by the denominator of the second fraction. It's like an inverse law. Don't worry about that, please, okay? Maybe some of you would have liked that background, okay? But do not divide by 2. Instead, multiply by 2, okay? The opposite of dividing by half would be doubling it, right? So do not divide by half when you're simplifying this, okay? Multiply by 2, and just to get rid of that, and then you can do everything else, right? So half times 2 goes away. Now you have 2 times EK is equal to mv squared. Okay, and I'm just going to show you why. Okay, so, and I can honestly tell you over like 50 times that I've seen students do this incorrectly. Okay, if you divide by, well, let's just say we're getting V by itself, right? So this is the error. This is an error. So do not do this. Okay, I just want to preface this. Do not do this. I've seen students go, okay, I'll just divide by 1 over 2m. Okay, so they do that, and then you get 1 over 2m. So v squared is equal to ek over 1 over 2m. Okay, right now, you are having, like if you don't enter this into your calculator properly, you will have the mass, so you're gonna make the mass half of it, right? Instead of doubling the kinetic energy. Okay? We want to double the kinetic energy and not halve the mass. Okay? So if you do this and you're not careful entering into your calculator, you're probably gonna get the wrong answer, which you don't want, right? So do not do this. Okay? Don't even think about that. Okay? Anytime you're getting rid of that the half, the fraction, this thing right here, multiply by 2, okay? Please, 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 do not try to divide by 1 over 2m, okay? Just multiply by 2. I know I just talked about that for 3 minutes, but I've seen that error so many times, so don't, okay? Alright, so we're isolating for velocity. So right now we have mass times velocity, so let's divide both sides by m. Now we have 2 times ek over m is equal to v squared. What is my last step to getting velocity by itself? Yeah, you bet. We definitely need to take the square root of that. Okay, so now we have velocity is equal to 2 times ek divided by mass. Okay, we know our mass, we know our kinetic energy, so we can just substitute these into our formula. So V is equal to the square root of, and again, be careful when you're entering this into your calculator. I would go 2 times 73 joules divided by your mass, which is 0.17 kilograms. And then you will get a value of 29.3 meters per second. What's wrong with this answer right now? Sig digs, good. I wanted to have only 2, so I look to the right of it. It's a 3, so I'm going to leave it alone. All right. How do we feel about kinetic energy and potential? Need to practice first, I feel like? Yeah.
Just curious, how did you get meters per second from that?
Okay, really good question. Okay, so a joule, we get kilogram meters squared per second squared, right? And we are dividing that by kilograms, right? Okay, so kilograms is in the numerator, right? So my kilograms will cancel here. So then I'll be left with meters squared per second squared, right? Okay, when you take the square root of that, your 2's cancel, and the square root will go away, and then you'll be left with meters per second. Yeah, really good question, okay? And again, you guys don't need to know how to do this unit, canceling your units, okay? It'll probably be helpful in this right here to find your meters per second, but for you guys, I think it's just more important that you guys know that velocity is in meters per second, energy is in joules, mass is in kilograms, okay? Really good question though. I appreciate that. Okay, and just lastly, before we finish the day, so let's just kind of summarize this. So we're going to talk about each of these motions. Is it kinetic energy or is it potential energy? So the swinging of a golf club. Kinetic or potential? Nice. How can it be potential, eh?
Well, when you bring it to the back, it's all potential.
Okay, sweet. So in my backswing, if I stop up here, then it's all potential, right? Yeah. And then as I go down, it is being transferred to kinetic. You bet. A book carried in a bag. Let's say we're not walking. So it's just potential? Yeah, good. So if we're just holding that book in a bag, it is potential energy, sure. A pulled bow. Potential, good. Electrical current of a wire. So like right now, so the electricity that is moving through our wires right now. Kinetic, good. And a vibrating drum head. Kinetic, good. All right.